Welcome to Ask and Learn.
Okay, so for this problem, a gas expands in two different ways. First, it's isobaric, and then it's adiabatic. And so we basically want to analyze the situation by drawing a PV diagram, getting the work, computing the temperature. Let's see, when did it actually ask for the temperature? Final temperature. So we just need the final temperature and then the heat flowing into or out of the gas. So let's start this one out by drawing our PV diagram. So here's P, here's V. And then first it expands isobarically, so we have a constant pressure. So here's our V naught. And then I'm actually gonna, let's see, erase this. Or actually, no. I'm gonna label this P naught because that's exactly what it is, and then relabel the axis. So here's P naught, and then this is my axis label. Oh, ran out of space. Okay. And next it expands isobarically to 4 V naught. All right. And this is like going to be really not to scale. Unless I erase this V naught. So here we go. Here we go. I can extend this axis and then double this distance. Let's put that right there. And if a gas is allowed to expand without any heat added, the pressure on the container is going to decrease. There's going to be less collisions kind of per second because the container is bigger, which is one way to think about it. Or you can kind of remember that this is what the adiabatic curves look like from studying the chapter. Great. And now we have the PV diagram, and we can go ahead and address the work done equals question mark. So the work is going to, of course, be the area under this curve. So to find this area, we need to find this. The square rectangular part is kind of easy. It's just going to be V naught times P naught. But this shape, we have to use the formula for it, which is given. I think it's around equation 19.24. I don't think it's exactly it. But you get an equation, but in the equation, you end up needing to find this final pressure. So in preparation for using this formula that I haven't actually written out yet, I just want to find this final pressure. And then I'm going to label each point. So here's your P3. Oops, not P3. I think I'm just going to label the points as 1, 2, and 3. So if I have a subscript, that's what they refer to. Here's 1, here's 2, and then there's 3. Great. So P3 we want to find first. And so to do that, you need equation 19.24. And if you do some a little bit of algebra, you get that P3 is the initial pressure divided by 2 V naught over 4 V naught. Where I'm using the equation that's where you have like an initial and final pressure for an adiabatic process, an initial and final volume, the initial volume being 2 V naught, the final volume being 4 V naught. And then of course that simplifies, but you could write it this way and you can actually sort of see where I got this number. And so you get this nice simple equation for that. And I guess the problem stated that there was a given heat capacity. So I'm just going to go ahead and not, it's not in terms of gamma. So I just want to put it in terms of CV instead of gamma. So as a reminder, gamma is equal to 1 plus R divided by CV, where R is the gas constant. And so then I'll go ahead and write that explicitly. So you have your 1/2 to the 1 plus R divided by CV. Okay, And now I did that little calculation. I think that's the only calculation. Okay, so now I can write out the work by formula. So the work by is going to be equal to the work done during the isobaric part plus the work done during the adiabatic part. And then the isobaric part, pretty relatively easy, P naught V naught, because that area, so the bottom of the rectangle is 1 V naught, the top of the rectangle is P naught. And then the adiabatic, so I'm going to use this formula given in the book, CV over R. And so you have your 2 P naught. Yeah, sorry, I'm trying to read my handwriting. There we go. P naught V naught, which represents the pressure and volume at point number 2, minus your P final, which is P3, which is P naught times 1/2 to the 1 plus R divided by CV. So I'll just like put a little arrow there. And I feel like I'm forgetting a term. Yes, I am. Multiplied by 4 V naught. What a kind of complicated equation. So our next one is, what is the temperature? Finally. Okay, so I was thinking of approaching this by finding the temperature at each point. And so yeah, let's start out with that. Let me just make sure there's no other givens. I see, T naught. They do give you T naught. Okay. So we know that T1 is T naught because that's what they give to us. And then so how do we find T2? So for an isobaric process, so you start with PV as an RT. For an isobaric process, P stays the same as well as N and R. You assume that you're not adding any numbers or not adding any atoms. So you can solve this for P over NR equals V1 over T1 equals V2 over T2. So then T2 equals, cross multiply and you get T2 is T1 times V2 over V1, and V2 is twice V1. So you got it's 2T1. So the temperature simply doubles going if you're increasing the volume isobarically. Let's see. Yeah, so T2 equals 2 T naught. And now let's get, I'm just gonna like label this C while I'm thinking about it. Okay. So that was like that little part. I'm just gonna section this off so it doesn't look like super messy. And then finally, you need to get the temperature after the adiabatic part. And so you can use one of the equations that relates temperature and volume for adiabatic processes. And here's what it looks like rearranged and applied to going from V2 to V3. So yeah, and then V2 we know is 2 times V3, V2, V3 is 2 times V2 because it's 4 V naught and 2 V naught. So then this becomes a half, and then gamma minus 1 from the formula on the last sheet is R over CV. Wonderful. So that's your answer. And then part D, the Q is wanted. So this one, we'd have to just worry about the heat added to the system for the isobaric part, because adiabatic means by definition that Q is 0. So That makes it slightly easier than if it were like isothermal. I guess delta U would be 0, which isn't that bad. Anyway, so just using our formula that perhaps you've used many times by now is the change in internal energy is Q minus the work done by the gas. So then you get Q is equal to work done by the gas plus delta U. We know that that's P naught V naught from the last one. And our delta U is NCV times T2 minus T1. And then we said T2 was twice T1, so it's going to be 2T1 minus T1, which is just T1. And so that's your P naught, V naught plus NCV T naught. I just want to double check one thing before I X out this video. Okay, that works. That's fine. There's no reason to simplify it or change it.